All right, let's talk about gravity. We're about to tackle a force that holds entire galaxies together, but it all starts with a surprisingly simple formula. In this explainer, we're going to go on a journey from Sir Isaac Newton's famous law to the much deeper and frankly cooler concept of gravitational fields. So let's get started. So here's the big question, right? We all feel gravity. It's what keeps us on the ground and what keeps planets spinning in orbit. But how do you actually translate that feeling into a precise mathematical model? One that works for everything. An apple, an asteroid, a distant star? Well, that's exactly what we're here to unpack. Our journey begins at the foundation, with Newton's universal law of gravitation. This is really the equation that started it all, the one that first described gravity as a predictable universal force. And the core idea? It's actually beautiful in its simplicity. Any two objects that have mass, you and the Earth and the Sun, even two tiny specks of dust in space, they are all pulling on each other. It's always an attractive force. It never pushes things apart. Now, this was totally revolutionary because it meant the very same force that makes an apple fall from a tree is what keeps the moon locked in orbit. This slide here breaks it down perfectly. So on the left, you can see the force is directly proportional to mass. You double the mass of one object, you double the gravitational force. Simple enough. But now look at the right side. This is where it gets really interesting. The force is inversely proportional to the square of the distance. What does that mean? It means if you double the distance between two objects, the force doesn't just get cut in half. Nope, it plummets to just 1/4 of its original strength. That's a huge drop. And here it is, that relationship in its famous mathematical form. The force of gravity, F, equals a constant, g, times the two masses multiplied together, all divided by r squared, the distance squared. And that r squared sitting there in the denominator, that is exactly why we call this an inverse square law. Now, the secret ingredient to this whole equation is that constant g. And just look at how incredibly tiny that number is, 10 to the power of -11. I mean, it's just mind-bogglingly small. This tiny value is exactly why you don't feel the gravitational pull of your computer or the person sitting next to you. For the force to be noticeable at all, at least one of the masses has to be absolutely enormous. We're talking planet-sized enormous. Okay, so let's take this universal law out for a spin. Let's see how it works in a really familiar scenario, the classic story of an apple falling to the earth. So here we've got two different ways to describe the exact same force acting on that apple. On the left, we've got our new, shiny, universal law of gravity. And on the right, you'll recognize Newton's second law, force equals mass times acceleration. In this case, the acceleration is just g, the acceleration due to gravity. Now, since both of these equations describe the very same force, we can set them equal to each other. And this is the aha moment. When we set those two equations equal, look what happens. The mass of the apple is on both sides, so we can just cancel it out. It's gone. This is actually really profound. It tells us that the acceleration an object feels because of gravity has absolutely nothing to do with its own mass. This is the math behind why a feather and a bowling ball fall at the exact same rate in a vacuum. And here's the proof in the pudding. This is what shows the theory works. When you take the equation we just made and plug in the known values for the constant g, the mass of the Earth, and the radius of the Earth, you get 9.8 meters per second squared. That's the exact value for gravitational acceleration we measure right here at the Earth's surface. It just works. But hold on. As powerful as Newton's law is, it leaves us with this really deep, kind of spooky conceptual puzzle. Gravity is a non-contact force. So, how does that even work? I mean, really think about it. There's no string connecting the Earth and the apple. There's no hand pushing it down. So how is that force transmitted across empty space? This whole problem of action at a distance really bothered physicists for a long, long time. And the solution to this puzzle is one of the most powerful and elegant ideas in all of physics, the concept of a field, or more specifically, the gravitational field. So the modern way to think about it is this. The Earth isn't directly pulling on the apple. Instead, the Earth's huge mass creates this invisible influence, a gravitational field that fills up all the space around it. The apple then just interacts with the field at its own location, and it's that interaction that creates the force we call gravity. This quote here from our source material just nails it. It's a two-step process. First, the mass creates a field. Second, that field exerts a force on another mass. This elegantly gets rid of that whole action at a distance problem. So how do we measure this field? Well, we define its strength, which we also call g, as the amount of force it would exert per unit of mass. And when you run the numbers, you find that the formula for the gravitational field strength is identical to the formula for gravitational acceleration. There are really two sides of the same coin. One describes the cause, the field itself, and the other describes the effect, the acceleration. Now, how do you visualize something that's invisible? Well, physicists have a couple of cool ways. The vector model on the left uses arrows. The longer the arrow, the stronger the field. But for our final mystery, that field line model on the right is way more intuitive. In that model, the strength of the field is shown by how close together the lines are. The more crowded the lines, the stronger the force. Okay, this brings us to the deepest question of all. We know gravity follows an inverse square law, but why? Why 1 over r squared? Why not 1 over r or r cubed? It turns out the answer has nothing to do with magic and everything to do with geometry. Let's just walk through the logic here. It's super clever. Step 1, imagine the Earth sends out a fixed number of these gravitational field lines, like spokes on a wheel. Step 2, as these lines travel outward, they have to spread out over the surface of a bigger and bigger imaginary sphere. Step 3, now just think back to basic geometry class. The surface area of a sphere grows in proportion to the square of its radius. So, step 4, if you have the same number of lines spread out over an area that's getting bigger by r squared, then the density of those lines, which is the field strength, has to get weaker by 1 over r squared. And that is the final amazing takeaway. The inverse square law isn't just some random rule that nature decided to follow. It is a direct, logical consequence of the simple fact that we live in three-dimensional space. The force gets weaker in this very specific way because space itself has 3 dimensions for it to spread out in. Which leaves us with a final, fascinating little brain teaser to think about. Based on the geometry we just saw, what if our universe only had 2 dimensions, like a flat sheet of paper? Or what if it had 4? How would that change the fundamental law of gravity? Something to chew on. Thanks for watching.